The spectrophotometer is a very simple machine. It has a bulb inside the casing that can emit light at specific wavelengths. The light shines across an open space and hits a photoreceptor on the other side of the space. The photoreceptor simply measures how much light hits it. So if nothing is in the open space of the spectrophotometer, the photoreceptor measures all of the light that was sent out by the bulb. The open space of the spectrophotometer can fit a square plastic or glass tube referred to as a cuvette. A sample of liquid is put inside the cuvette, and the cuvette stands inside the space of the spectrophotometer. The light sent out by the bulb now passes through the liquid before it reaches the photoreceptor. Anything in the solution can cause the light to reflect away from its direct path toward the photoreceptor. The photoreceptor now reads the amount of light that makes it through the solution. It calculates how much light was reflected or absorbed, and the reading is displayed as absorption of light. The more molecules you have in your solution, the more light is blocked from its path, so the reading will be higher. Different molecules reflect different wavelengths of light. The spectrophotometer can adjust the light that it emits so that one or another wavelength can be sent through the sample at a time, and the absorption can be measured. DNA optimally absorbs light at the 260 nanometer wavelength of light. Proteins can absorb at the 280 nanometer wavelength, but proteins can also absorb at the 260 nanometers. So if your sample has protein contamination in it, then the absorption will be higher, and it will look as if your sample has more DNA in it than it really does. This is why we check the absorption at more than one wavelength in order to compare the absorption and determine whether the sample is pure or not. The nice thing about DNA is that it absorbs light at 260 nanometer wavelength very predictably. Someone actually made a standard curve of spec readings, referred to as optical density, or OD, versus DNA concentration, and the slope of the line was 0.02. So the equation of the line is y equals 0.02x, where y is the optical density at A260, and x is the micrograms of DNA per milliliter. If you want to know your DNA concentration, you take your A260 reading and divide it by 0.02. Or, since dividing by 0.02 is the same as multiplying by 50, you can multiply your A260 reading by 50, and you will have the concentration in micrograms per milliliter. Here's an example. If your A260 reading is 0.329, then your sample has 0.329 times 50 equals 16.45 micrograms per milliliter of DNA in the sample in the cuvette. Now, let's combine what we know of dilution factors from the first lab of solutions and dilutions with what we know from spectrophotometric readings of DNA at A260. Let's say we had 0.25 grams of fish, that's 250 milligrams of fish, and we ground it up in lysis buffer and heated it and mixed in some more salts and chilled it, and we ended up adding a total of 1.5 mils of liquid to our sample. After centrifugation, we transfer all of the aqueous supernatant into a new tube and added 1.2 mils of ethanol to precipitate the DNA. After the DNA pellet is dried, we don't have any liquid at all, and the DNA pellet is resuspended in 500 microliters of water. The sample is diluted in more water using 200 microliters of the DNA sample and 800 microliters of water. The diluted sample is measured in the spectrophotometer at A260, and the absorbance reading is 0.592. First, we determine the concentration of DNA in the cuvette, which is the diluted DNA sample. 0.592 times 50 equals 29.6 micrograms per milliliter in the diluted sample. The dilution factor of that sample was 200 plus 800 is 1,000, divided by 200 equals 5. So the resuspended DNA sample has 5 times 29.6 micrograms per mil of DNA. That is 148 micrograms per milliliter. The sample was resuspended in 500 microliters of water. That's equal to a half a mil of water. Now 0.5 mils times 148 micrograms per mil equals 74 micrograms of DNA in the pellet. Since the DNA pellet was from all of the supernatant from the entire fish, then so long as all of the DNA was released, we have 74 micrograms of DNA in 250 milligrams of fish. Notice that the initial liquid added during lysis didn't factor anywhere. This is because we eventually got rid of all the liquid volume when we dried the DNA pellet. So the only numbers we care about are the initial weight of the sample and the volume that the DNA pellet was dissolved into, and then any dilution factors after that.